This is ISCI 2001, Chapter 18, Earth's Waters. The themes for this lecture include water on Earth, which includes freshwater, surface water, groundwater, and freshwater as a resource. We'll also be discussing seawater with the oceans and seas. Water covers 70% of the Earth's surface, and 97% of Earth's water is stored in the Earth's ocean. Ocean water is too salty for human consumption and agricultural uses. Basically, what would happen if you drink seawater or ocean water is it is a hypertonic solution, which means it's going to draw all of the moisture in the water out of your cells, causing you to dehydrate. Once you reach extreme dehydration, your body will shut down. It will no longer maintain homeostasis. All other water that is fit for human consumption and agricultural is called freshwater. About 2/3 of Earth's freshwater supply is locked up in the ice caps of Greenland and Antarctica and in glaciers. This leaves less than 1% of all the water found on Earth is available freshwater. So less than 1% of the water found on Earth is fit for our consumption. Here you see Greenland, you also see Antarctica, and you see the glaciers. This is where basically almost all of our fresh water is stored up. If we ever got to a point where, we were at extreme need for fresh water, we could go and basically harvest water from the ice cap. So it's not like it would be an impossible feat. It would cost more money, therefore making water costs more money. But we do have a large percentage of our water locked up here in these ice caps. Evaporation of water from the ocean is important because water vapor leaves salt behind, forming precipitation that is fresh water, and the water vapor is transported into the atmosphere. This natural desalination process produces and transports enough fresh water to cover the entire Earth with a layer about 33 inches deep. So it's quite a bit. This cycle of evaporation, precipitation, and return of water to the ocean is called the hydrologic cycle, and we discussed it in our last lecture. This is a picture of the hydrologic cycle. You can see on the right-hand side from the ocean the evaporation, then it condensates. The latent heat of the atmosphere condensates the water into clouds. Also, there's radiative exchange. There's all sorts of the solar heating. The clouds move throughout the sky. Then when it reaches its saturation level, or if the balance of the saturation level is off, or the saturation equilibrium is off because of temperature change or air pressure, that's when the clouds and the water vapor actually release into precipitation. The precipitation can either be the rain, like you see about midways of the picture, or to the left you can see the water storage in ice and snow up on the top of the mountains. We've got a lot of things that happen as far as surface runoff, infiltration, the percolation, soil moisture, soil heterogeneity. So you've got a lot of things, and all of this water is going to run through the actual ground back into the streams and rivers. Also, you can see where the radiative exchange is, where it's pointing to the ground. Those are crops, and you can where all of those plants are planted. There's definite evaporation coming from them also, so that's one type of evapotranspiration, or transpiration, excuse me. And so there's many ways for this cycle to occur, either through the plants or the water, and with that water evaporating and condensating and then precipitating. Most fresh water comes from precipitation. Evaporation plays a role, and about 2/3 of rain is evaporated back into the atmosphere. The remaining water flows downhill to areas that are low or soaks into the ground, and water moving across the surface is called runoff. Runoff can form streams. Water that soaks into the ground moves downward into a saturated zone and is now called groundwater. If you could follow the smallest streams downhill, you would find that it eventually merges with other streams until they form a river. The land area drained by a stream is called the stream's drainage basin or watershed. The water of streams, ponds, lakes, and reservoirs is collectively called surface water. Precipitation soaks into the ground or percolates slowly downward until it reaches an area or zone where the open surfaces or the open spaces between rock and soil particles are completely filled with water. Water from such a saturated zone is called groundwater. There's a tremendous amount of water stored as groundwater, which makes up a supply of about 25% larger or 25 times larger than all of the surface area of surface water on the earth. Groundwater is an important source of fresh water for human consumption and for our agriculture, and groundwater is often found within 330 feet of the surface. So this is when you can drill wells and that kind of thing to hit that groundwater or the water table, we also call it, but it's going to be within that 330 feet range. Here you can see, let's start up at the top where the buildings are. You've got urban runoff and leaking sewers. It can get down into the ground. The landfills and the petrol stations, they're definitely seepage going into the ground. The oil tank storage, the industrial storage and contaminated lands, all the pesticides, fertilizer applications, all of that is going to seep into the ground. And when it seeps into the ground, it will get into our groundwater and it will pollute it. So we have to be really, really careful because, and you can even see where the house is, the septic tank is going down and there's a well dug right there and it's going into that water. So we need to be very careful about the things that we're putting on our plants and on our ground, because any pesticide or chemical that leaches into the ground is going to go into our groundwater and then it's going to come up in the water that we drink. Even if the water is treated by the water treatment facility, it's not going to be able to get all of that out. So the more contaminated the land is, the worse the water is going to be in that area. If you think about when you travel to different cities and their water tastes different, it's not because of the treating process, it's because of the stuff that's already in the water. So that's definitely something to think about. Fresh water as a resource. It's estimated that each person around the world uses about 150 gallons of water per day. That's for things like agriculture or electricity, industrial purposes, but it's also for, bathing. It's for cleaning. It's for brushing your teeth and washing your hands. That's a lot of water that we go through each day. It's estimated that each American uses about 1,500 gallons of water a day. So when you think about that, that's like Americans are being very, very wasteful. If you look at the percentage of the American uses compared to the world's uses, you've got 150 gallons versus 1,500 gallons. And that's an extreme amount. And I mean, think about it. We wash our cars. We spray our houses down. We water our lawns. We use all of this water like it's a commodity that's never going to go away. And we need to really consider how we're using it and how wasteful we are with it in comparison to the rest of the world. Most of the water supply is obtained from surface water resources of streams, lakes, and reservoirs. At 37% of the municipal water supply comes from groundwater. Here you've got, if we start at the top, you've got chemical additions to the water. You've got the intake, the coagulation, and basically what happens is they add the chlorine, the lime, the alum, and they mix it so that it gets some of the impurities out. Chlorine it kills bacteria. So I mean, once it goes through that process, then it goes through the sedimentation, which is where all of the solid particles in the water, go to the bottom. The water is suctioned off the top. Then it goes through the filtration process. It's got several different layers that it has to go through, starting with very coarse objects at the top, like rocks, charcoal, that kind of thing. At the very bottom, it's very fine. It's sand. Then it goes into your storage. And in storage, it's also disinfected. And then it's distributed. So just remember, when you're drinking water from a public water supply, there are chemicals added to it to make it safer for you. If they didn't add those chemicals, basically our water would be unfit to drink. More than 70% of the surface of Earth is covered by seawater, with an average depth of 12,500 feet. We are called the blue planet because the majority of our Earth is covered in water, and those are our oceans. And it would be nice if we were able to drink all of the water, but obviously we can't because it's ocean water. But if it didn't have that salt in it, we would see lots of issues with bacterial growth. We already have algae growth, but it would be a lot worse if it didn't have the salt in it. So the salt is actually necessary for us to be able to maintain life here. The ocean is a single continuous body of salt water. You've got the Atlantic, Indian, Arctic, and Pacific, sometimes the Southern. So, you know, even though we call them different oceans, they're one solid ocean. There's nothing that's separating them from each other. A sea is usually a smaller part of the ocean, a region with characteristics that distinguish it from the larger ocean of which it's a part of. So you can see on the left-hand side, you've got the Pacific Ocean. Then in the middle, you've got the Atlantic Ocean. Then on the right, you have the Indian Ocean, and then back to the Pacific because our globe is round. But you can also see the different types of seas, and these seas are still part of the oceans. You've got the Weddell Sea down in Antarctica. We've got the Gulf of Mexico, the Caribbean Sea. We've got tons of them: Beaufort Sea, Hudson Bay, Caspian Sea, Black Sea, Mediterranean Sea, Baltic Sea, North Sea. I'm not going to read them all, but you see basically the point of these seas are still part of our oceans. We just call them seas because they're more blocked off a little bit. So with our standards, what we covered was the hydrosphere. We were able to demonstrate a basic understanding of the water cycle. We were also able to measure and describe changes in the weather, how they relate to the water cycle, and the position of the Earth and the Sun. We also talked about the biosphere. We were able to recognize and describe different biomes and how they are affected by weather, plant and animal activity, and geologic processes. And keep in mind, even though we didn't talk about like individual specific biomes like rainforest, deciduous forest, tundra, taiga, desert, that kind of thing, we did talk about the different animal and plant activities, such as the hydrologic cycle, and how we humans, you know, we are animals, how we affect that cycle by putting in pesticides and different types of chemicals into our groundwater.